Hi everyone, welcome to this session on fast distributed training and linear scaling with distributed data parallel in Amazon SageMaker. My name is Aditya Bindal. I'm a senior product manager with AWS. We're going to talk about distributed training today. We'll talk about some of the challenges developers face when they need to use data parallelism, when and how they would use data parallelism, and then we'll talk about the new capabilities we're launching in SageMaker to make distributed training, specifically data parallel training, easier for you and more performant. We'll end with a deep dive example showing you how you would use these new capabilities in TensorFlow and PyTorch. So let's start with why you would use data parallelism, when you would need to use this. And a common complaint amongst TensorFlow and PyTorch developers is with state-of-the-art models in natural language processing and computer vision, training times are very long. It can take days, even weeks to wait for training results. And this is a big problem for data scientists because they can't iterate on the next version of their model until they have results from the previous iteration. So now 4 or 5 days long training jobs are slowing down the entire development cycle and delaying the time to market for their ML application. So let's talk about the value proposition and the economics of distributed training. When would you, and what's the benefit of going from a single node, a single GPU instance like the P3DN 24x large, to a cluster of nodes with multiple P3DN 24x large instances? So in an ideal case, if it takes you 8 hours to train a model with one machine, it should take you 1 hour to train that with 8 machines. But in practice, you don't scale perfectly. And we'll talk in a few minutes about why that's the case. Your scaling efficiency, which we measure as the percentage of the ideal linear scaling you would get if you went from that 8 to 1 example we just talked about, in an ideal case, that's 100%. But in reality, it's not 100%. So for example, if you have a scaling efficiency of 90%, then going from 1 to 8 nodes will decrease the training time by 86%, but increase the cost by only 11%. So the higher your scaling efficiency, you don't have any trade-off between the training cost and the training time. When your scaling efficiency is low, you have a trade-off between cost and time. And a key challenge for developers doing multi-node training, distributed training, is making sure that scaling efficiency number is as high as possible. So let's do a quick overview of how data parallelism works. The core idea is that you parallelize training by giving each GPU a replica of the model. In this example, we have a simple 4-layer neural network model, and each GPU has a complete copy of this model. And then each GPU gets a subset of the training data. So we take a mini batch and we pass it different mini batches to different GPUs, and they process the model and train the model on their slice or subset of the training data. And you can then scale this idea and do it with more GPUs. So in this example, we now have 4 GPU devices. Each GPU has a complete copy of the neural network model, and each GPU device is training on different subsets or slices of the data. But if each GPU is training my model in a different subset of the data, how do we reconcile and get one single model after each iteration or each step? So we need a way to synchronize gradients across machines. And there's really 2 approaches here. One is parameter server, and parameter servers were the dominant way of synchronizing gradients. TensorFlow originally had parameter servers as their design for distributed training, and the way this works is each worker node will pull the model from the parameter server, train with its mini batch, and then push a new version of the model back up. Each worker node will do this. The parameter server or the set of parameter servers will then average out the gradients across all the workers and then make a new updated model available. The problem with this approach was that it resulted in an imbalance in the amount of data that was being sent and received from each parameter server. And this caused bottlenecks and made the system less stable when you increase the size of the cluster. So we went to a different paradigm, borrowing from the HPC community and their work on parallel computing with things like MPI. We started using all-reduce algorithms. They got rid of these dedicated parameter servers, and instead the GPU instances would communicate with each other directly using typically a ring topology. So this addressed the latency and stability challenges of parameter servers, but it didn't efficiently utilize the bandwidth that's available in AWS. And what we did is we challenged our teams and we said, let's try and come up with a better solution for gradient synchronization. Let's see if we can take the best of both worlds and pick and choose from what works well in parameter server and what works well in these ring all reduced mechanism. And that's exactly what we came up with. But before we do that, let's dive a little bit deeper in what's really hard for developers about data parallelism. So the first thing is infrastructure. Before we get to the neural network algorithm, in order to do multi-node training, you have to provision a cluster of GPU instances. They all have to be connected to each other with a high-performance network, and they need to be connected with your I/O solution. So that could be training data in S3, Amazon's Elastic File System, or FSX for Lustre for a distributed file system. And then on top of that, you need a software stack of the machine learning framework, low-level libraries, and hardware drivers that are all performant and constantly change, and you need to keep up with them. So the first challenge for developers is just creating the right environment in which they can launch their training jobs before they get to performance. The next challenge is performance itself. Now, typically in a neural network model, you have 4 components, or you can think of the mental model of training as 4 different components. You have a forward pass, a backward pass, the all reduce, and optimize steps. And on GPUs, the forward, backward, and optimize, as you get more and more GPU instances in your cluster, will remain the same. What ends up taking more and more time as the cluster becomes larger is this all reduce step. So when you have a very large cluster of machines, you now need to synchronize gradients between all of them, and that creates a bottleneck. So eventually this all reduce becomes the longest process in your overall neural network, and this ends up becoming a bottleneck, going back to the original idea of scaling efficiency, which this hurts. So if we look at how state-of-the-art solutions scale today, as you increase the number of GPUs, your scaling efficiency starts to fall because that all reduce step is now taking longer and longer. So once we get to 512 GPUs, my scaling efficiency to train BERT large using these ring all reduce algorithms falls to just over 50%. So to solve these challenges, we built SageMaker distributed data parallel. And to give you some context on how we built SageMaker distributed data parallel and why we built it, this year at SC20, we presented a paper on rethinking the parameter server at scale on the cloud. And the core thesis was we could go back to some of the innovative work that was done by researchers both in the parameter server paradigm, but also the ring all reduce MPI paradigm. And we could take the best of both worlds and innovate and build a solution that works well for both. Now, we have used this underlying technology to demonstrate the fastest training times in the cloud for a few years now at reInvent. In 2018, we demonstrated the fastest training time in the cloud for ResNet. Last year at reInvent, we did the same thing again for BERT and MOSCAR CNN. And this year, just this morning, in fact, you would have seen the fastest training time for T5, the 3 billion model in NLP, as well as MOSCAR CNN again. So what we've built is that same underlying technology, but we challenged our teams to make that available to all developers through Amazon SageMaker with a very easy-to-use API that automates a lot of the performance tuning and complexity we've talked about beneath the hood. So it's a library for distributed training of deep learning models in TensorFlow and PyTorch, and it speeds up your training jobs when your bottleneck is network. So when you're network bound, this will make your training cheaper and faster. And we've built this from the ground up to fully utilize AWS infrastructure and topology, leveraging the node-to-node communication between EC2 instances that's available. And this is a key point because a lot of the all-reduce algorithms or the parameter server implementations are specific to a slightly different topology and infrastructure. And we've been able to exploit more performance from your algorithms, from your training models, by building something that's highly performant and tuned for what AWS offers. We see that SageMaker Distributed's data parallel is 20 to 40% faster and cheaper than the alternatives developers use today in TensorFlow and PyTorch using NCL and MPI-based solutions. So how does it work? Well, the first thing you'll notice when you launch a training job with SageMaker DataParallel is the CPUs on your GPU instances become parameter server. So SageMaker's control plane will create your compute cluster of P3DN or P316X instances, and then the CPUs on these instances act as parameter servers. Next, we introduce a new technique called balanced fusion buffer to make optimal use of bandwidth. So a buffer in the GPU holds the gradients until they hit a certain threshold size. And we then copy the fuse buffer onto CPU memories, sharded into n parts for each node in our cluster, and then we send the ith part to the ith server. So what this does is it equalizes and balances the amount of data that's being sent and received from every parameter server in your compute cluster. And if we go back to one of the biggest challenges we talked about with traditional parameter servers, it was this imbalance in the amount of data that was being sent back and forth to parameter servers that created the bottlenecks and the instability. So that's really what we've gone back and reimagined for the parameter server, and that's how we generate a faster all-reduce and a more stable all-reduce in TensorFlow and PyTorch. Now, another benefit of offloading the all-reduce operation or the gradient synchronization operation from GPUs to CPUs is that we can now overlap the backward pass and the all-reduce step. So that reduces your overall step time even more and frees up GPU resources so you can improve GPU utilization through other means. Architecturally, there's no change in how you use SageMaker to train models when you enable DataParallel with SageMaker Distributed. So your training data are still in S3. You create a training job using the SageMaker Python SDK and the framework estimators. And when the job completes, you have a save model artifact in S3 that you can deploy with SageMaker hosting. So let's take a look at how SageMaker DataParallel performs on popular NLP and CV models. So we've taken two examples here, BERT, which is a popular natural language processing model used by our customers, and Mask RCNN, which is a popular instant segmentation model used by our customers as well. And we've shown you benchmarks here with 4-node and 8-node P3DN 24x large clusters. Each machine has 8 V100 GPUs with 32 GB memory. So on a 4-node cluster, BERT throughput improves by 52%, and the scaling efficiency goes from 55% to 84%. And I really want to focus on that second number here when we make scaling efficiency increase from 55 to 84%. At 55%, you're adding more compute, but almost half of that is being taken away as an overhead or tax in the network communication. When you can improve scaling efficiency to 84%, you no longer have a trade-off between time and cost. As long as you have an algorithm that can converge with larger batch sizes, you can scale out horizontally and iterate faster. You can reduce things that would take days to mere minutes or hours. Now, when we designed SageMaker Distributed DataParallel, we wanted to provide a native framework experience that requires learning no new terminology and concepts. So we wanted you to use the same API specification and terminology that you know and use today in TensorFlow and PyTorch. So in TensorFlow, SageMaker DataParallel uses Horvath APIs, or a specification very similar to the Horvath APIs, and in PyTorch to DDP. So this ensures that you can continue using the same specification, you can write your training scripts in the same way, and we fit into that and map one-to-one instead of introducing any new terminology or concepts. Okay, so with that, let's dive right into an example. So we're going to use the new data parallelism library and engine in SageMaker Distributed to train a model with PyTorch. So the first thing we'll do is we'll modify the PyTorch estimator in SageMaker to enable SM Distributed Data Parallel. So if you've seen the PyTorch estimator before, you specify a name for your job, source directory, you point to where your training script is saved, you indicate the version of the framework, in this case PyTorch, that you want to use, and then the instance count and the instance type. And the only thing that changes here is this distribution argument. In the distribution argument, we will say that we want to use SM Distributed, and we want to use the data parallel engine, and that's what we want to enable. Nothing else in your estimator needs to change. The rest of it stays the same. So now let's dive into what we actually need to change in the training script. So the first thing we'll do is import SM distributed data parallel library and initialize it. If you've used DDP in PyTorch, this should look identical and intuitive to you because it's using the exact same specification and flow as DDP. No changes are required to your model definition, your core training loop, or your evaluation. All of that stays exactly the same. SageMaker's data parallel library does not touch any of these things. Now let's go through the other code changes that you need to make. All of these are places where you would replace DDP with SageMaker data parallel. So in this example, we point out some of the areas where you were previously using DDP and now you would use SageMaker data parallel. So first, we scale the batch size by the number of processes. Then we set the number of replicas to the number of workers, and we also set the node rank. We wrap the model with our version of DDP that's available in the SM distributed library, and then we pin each GPU to a single SageMaker data parallel process. Finally, we save checkpoints only on the leader node, and if you've used DDP, all of this should look identical to what you do today. And that's it. Those are the only changes you need to make. Once we've made those modifications to the SageMaker framework estimator and to the training script, you get to enjoy all the performance and stability benefits that we've talked about. So now let's walk through a similar example and we'll modify a training script for Albert in TensorFlow to use SageMaker's data parallel library. So we'll start at the same point. We'll take the TensorFlow estimator in SageMaker and we'll make some modifications to it to enable SM distributed data parallel. So everything else stays the same. The entry point where your script is saved, the version of the TensorFlow framework that you want to use, the size of your cluster, and the type of instances that you want to use, whether it's P3DN 24x large or the P3 16x large. And then we would provide this distribution argument again, just like we did with PyTorch. And in this argument, we would indicate that we want to use SM distributed using the data parallel engine. So now let's dive into what we need to change in our Albert pre-training script. So the first thing we do, once we've imported TensorFlow as our framework, we would import SageMaker distributed data parallel, and within that we would import the TensorFlow library and call that SDP, and we would then initialize. So again, if you've used Horovod with TensorFlow, this should look identical and intuitive to you. Similar to PyTorch, there's no change you need to make in how you define your model, how you compose the neural network architecture, the core training loop, evaluation, all of that stays exactly the same. We've designed this in a way that makes it identical to the experience you have using TensorFlow and Horovod today. The one thing we will do, which is needed for any distributed training workload, is to adjust our learning rate, just the way we adjusted our batch size previously, by the number of workers, and we'll use stp.size to get the number of workers. So now let's talk about the other changes to the training script, where we would replace Horovod with SageMaker data parallel in the rest of our training code. So we first pin each GPU to an SDP process with local rank. Then we wrap TensorFlow's gradient tape with our own distributed gradient tape. And finally, we broadcast model variables from the leader node to all the other worker nodes. And similar to PyTorch, we'll again only save checkpoints from the leader node. We won't do it from all the worker nodes. And that's it. Once we've made these modifications to the Python SDK and the estimator in SageMaker, as well as to our Python training script, we're ready to use SageMaker data parallel and launch our training job on a cluster of P3DN 24x large or P3 16x large instances. So if you've used Horovod with TensorFlow, this should again look very similar and intuitive to you. We followed exactly the same pattern that our developers use today to give them a seamless way to try SageMaker distributed data parallel and to use its capabilities. With both PyTorch and TensorFlow, once you've made these modifications and launched the job, you get all the performance and stability benefits that we talked about. The complex tuning and optimizations and network optimizations that we've done behind the scenes are now available to you. So before we wrap up, I wanted to share a little bit about some customers that are using SageMaker Distributed today. And this is a story that we're really excited about. So Turbine AI is a simulation-driven drug discovery company, and they deliver targeted cancer therapies to patients. So they use machine learning to accurately predict interventions at a molecular level and discover new cancer drugs. So for them, iterating quickly is very important because it allows them to get to that discovery point and that intervention point faster. And a big pain point for them today is it takes days to train these models that are used in simulation. And if we can decrease the time it takes to train these models from days to hours, it allows their science teams to iterate daily instead of weekly. And in getting drugs to market and getting to discovery, this is crucial. So we're very excited that Turbine AI has been using SageMaker Distributed, and they expect their training times will actually decrease by up to 90% using these new DataParallel capabilities that we just talked about. Finally, we talked about data parallelism today. We're also launching a new capability in SageMaker Distributed for model parallelism. So in data parallelism, as we talked about, each GPU device has a complete replica of the model, and then we split the data across multiple GPU devices. But there are some cases increasingly in natural language processing, but also in recommendation models and GANs and computer vision, where the model itself is so big, or the model and the inputs themselves are so big that they don't fit in a single GPU's memory. For those use cases, you need to use model parallelism, where the model graph itself is partitioned across multiple GPU devices. And SageMaker Distributed today is also launching a new capability and engine for model parallelism that would automatically and efficiently split your model across multiple GPUs and set up an efficient pipeline to execute across multiple micro batches. So that session is AIM 405, and we would love for you to join that as well. So to summarize, SageMaker Distributed is a new managed distributed training capability. In this session, we talked about data parallelism. And with the data parallelism engine, you can reduce your training time and cost by leveraging the optimizations we've made at the network level, ground up, to make full utilization of the infrastructure and topology offered by AWS. We support and tightly integrate with TensorFlow and PyTorch and Horovod, the frameworks that our customers use today. And we also have another capability that we would talk about in the AIM 405 session for model parallelism. And with this new capability, anyone can now train large neural network models that don't fit a single GPU's memory. So we automatically and efficiently partition the model. You need to make minimal code changes to your TensorFlow and PyTorch training scripts, and we efficiently pipeline the execution of the model's operations in a way that maximizes GPU utilization. So thank you so much for joining this session. We hope you found it useful. Please stick around for a survey at the end. Thank you.